Yeah, good morning, good afternoon, good evening, wherever you are. Welcome to today's webinar on the topic of predictive maintenance, current market trends on the road to zero unplanned downtime. My name is Knud Lasse Lueth. I'm the CEO here at Iot Analytics, and I will guide you through today's webinar. Just very quickly, there have been so many webinars, so I'll do it very quickly. We do a 1-hour webinar. Everybody is muted. We will have substantial time at the end for Q&A. If you have problems, please let us know in the chat. A replay will be sent to you by your email. And at the end, it would be really good if you could let us know how you liked the webinar and what we can improve next time. With that in mind, just quickly, who's on the call today? Besides me, there's Fernando, who will be presenting some of our research that he's recently led on the topic of predictive maintenance. And then we have a team from PARC, which is a Xerox company, Markus and Vats, and both have looked at the topic of predictive maintenance for years now and have quite a lot of experience, and will share some of their stories and some of the things that they've seen in implementing predictive maintenance with their various clients. Very briefly, just so you understand who Iot Analytics is, we are a market research firm for everything Internet of Things and Industry 4.0. And we typically operate with writing reports on different topics. And we will present a number of insights from the latest predictive maintenance report. And obviously, then we have additional research services as well. Yeah, and then starting with predictive maintenance, we looked at this for the first time. Actually, we looked at it in 2016. And to be honest, when we attended fairs in 2016, I attended a fair on maintenance. Predictive maintenance was nowhere to be seen. Nobody talked about it. But it was clear that there was this IoT and AI conversion. So we started talking about it. We had our first market report in 2017. And we continued to cover it. We had a second report in 2019 on the topic. And so just recently, a couple of weeks ago, we released our third report on the topic of predictive maintenance. And we will present some of the findings of that report in today's webinar. Obviously, not all of them, but hopefully some of the ones that you find very relevant for whatever you're doing and however you're approaching predictive maintenance. And so with that in mind, we will talk about predictive maintenance, the evolution, and go into the market overview and trends. And then the team from PARC, Markus and Vats, will talk about how they approach the topic and some of the lessons they've learned on the way to zero unplanned downtime. Let's get started with, I always like to start with Google Trend, which is very, it's a very widely used tool, but it gives you some ideas of what people are looking for. And you can see that predictive maintenance as a topic has really had a steady rise in search interest, where preventative maintenance, which is a slightly different technique, and we'll get to that in a second, has been declining quite a bit over the years. And so for us, how we define predictive maintenance is a set of techniques to accurately monitor the current condition of machines or any type of industrial equipment with the goal of predicting upcoming failures, ideally before they occur, by using automated near real-time analytics and advanced statistics or supervised, unsupervised machine learning. And so if you look at it from a point of view from maintenance, there are obviously different strategies. If there's no strategy, it's reactive maintenance. There's a failure, and you see it after it has occurred. Pretty much all companies in the world today have preventive maintenance, where they have a schedule when they know when to look at what machine and so on. Some go further into proactive to kind of go into root causes. What has led to this? The left-hand side is typically not necessarily sensing technologies behind it. On the right-hand side, you see the ones that have sensing technologies. And so condition-based maintenance is something we've actually had for decades. That is not really new. So sensing technique supported maintenance, especially on vibration and rotating equipment. But predictive maintenance really goes a step further, where it's about the about more advanced statistics, about combining different sensor values, looking into machine learning and looking at past data. And so there's quite a bit more in predictive maintenance. And then you hear some people talk about prescriptive maintenance, which, especially in the last year or two, I would say this topic has picked up, where it's more about going beyond the prediction and saying why did it fail, or what needs to happen after the prediction. And so you automate the workflow entirely, essentially. So we can look at it as a couple of examples here. So let's look at a motor. And so the motor is vibrating. So let's assume we're doing different types of sensing. So right here, this is the typical operation. Then after a while, some kind of vibration begins, and you could start to sense it. And these are days here that are depicted. So then at some points, you see some evidence that something is wearing off. The performance declines, you hear noise, it's starting to get hot, and then the motor fails at some point. And so that is kind of a typical thing. So in a reactive maintenance, you would be here after failure, you would do something. In a preventive maintenance, there's case one where you had a routine check on day 23 before the failure, and you missed and you did not detect it. Well, you may not detect it. So then again, it's reactive maintenance. Or in another case, you had a routine check and detected it, and then you solve it. In condition-based maintenance, you have some predefined that the vibration here, for example, if it reaches a critical value, say here, hey, if light flashes, I know I need to do something. So in this case, you would have caught it, and the event was preempted. In predictive maintenance, well, it depends a little bit how good your predictive. And we're going to talk about today how good predictive maintenance algorithms. In predictive maintenance, you start to maybe see something happening, and ideally your algorithm is already calculating remaining useful life, hopefully accurately, and you have the time here to react. So you can decide whether you want to react now or maybe in 2 days, because it doesn't seem like a big problem just now. So it gives you this flexibility. It's not always remaining useful life, but very often. And so let's move a little bit more to our survey and research data. So we obviously asked people that have, and we've talked to quite a few that have done predictive maintenance in the last years, what is so valuable about it? So here's a quote from the chemicals industry. Predictive maintenance models have allowed us to refine our preventive maintenance schedule. So we just saw preventive maintenance for our critical equipment, eliminating unnecessary downtime. We're also reevaluating our organizational structure to streamline the cost and effectiveness of our maintenance and reliability teams. The final value around predictive maintenance program was to help offset the high turnover rate in the US Gulf Coast region, where employee retention for skilled engineers is an issue due to the competitive market situation and dense population of chemical plants in the region. So this is a very specific problem, but again, here you can see that predictive maintenance has the effect of really reorganizing. Companies are reorganizing their maintenance based on that. An example from the automotive industry, achieving real-time accurate predictive failure analytics has truly allowed for zero unplanned downtime on mission-critical machines and processes. And so I think that's, in some of the discussions we're having, that's interesting, because it's really not about a 5 to 10% increment on the unplanned downtime. Companies are talking to going from whatever value it is today to hopefully near zero in the future. And it doesn't seem completely unrealistic that someone would get there. And lastly, an oil and gas example, predictive maintenance enabled us to actively monitor highly critical assets, provided us with multiple feeds of various data points, temperature, vibration, throughput in this case, allowed us to perform analysis of the asset health in real time. I think that's important, and helped us to prevent the need for reactive actions for critical assets. And so they show these comments show you that the value is real. And we, as a research company, obviously try to understand how big is the market and how much is it growing. So in our latest analysis, we think that predictive maintenance is in 2020 about a 5.5 billion market. And despite COVID, in our view, we've seen a growth. It was slower than the years before. I mean, we heard a lot of projects were stopped, but nonetheless, a lot of companies continued, and it was growing. And then I think for the future, for various reasons, I think there is reason to believe that this is quite a growing market. Some people call it the killer use case in IoT, or one of the. And based on the data that we've seen in the surveys, that is certainly not far from the truth, at least what the data tells us. And with that, I will hand over to Fernando, because he has, well, he's going to present some of the survey results that we've done with users of predictive maintenance.
Okay, thank you, Knud. Hello, everybody. Yes, as you rightly pointed out, I'm going to present some of the interesting findings that we collected from a survey that we conducted on Q4 last year. And the survey collected information from senior IoT, OT decision makers at various industries. So one of the main insights we collected is that the market potential is high. Well, we can see here that only 6% of manufacturers have rolled out PDM. If we consider the top categories, we can see that almost 28% has already either fully or partially rolled out predictive maintenance solutions. And at the same time, if we see all the rest of the categories, we can see that many others are looking to implement predictive maintenance solutions. If we move forward to the next slide, yeah, thank you. So now the question is, from those that have rolled out predictive maintenance, what are the benefits? What are the return of investment? We can observe here that most of them, almost actually more than 80%, had reported an extremely positive return on the investment, with almost 45% of them amortizing the solution in less than a year. And this has been further backed up with some quotes that we collected from the interviews during our research. And both of the quotes that we have here back up the idea that predictive maintenance generate positive return on investment within the first 6 or 12 months. If we move, yeah. So the next question or the next insight that we collected was, what are the associated costs to these unplanned downtimes that actually predictive maintenance is meant to reduce? And we observed that when we consider entire factories can experience up to 144 unplanned standstills in a year, which translate in times into almost 18 hours in a year. And we also analyze what are the direct and indirect costs of these unplanned downtimes. Direct costs usually include spare parts and personnel or external support, and indirect costs reflect the loss, the profit and the loss impact of those standstills. And we can see that the indirect costs are really high, and altogether can sum up to factories losing almost 2.3 million in a year due to these unplanned operation standstills. So on this respect, predictive maintenance can help to reduce this huge economic impact of unplanned operation standstills. And the last slide, we collected information on what was the most used analytic method by our respondents, and we observed that supervised machine learning is the most popular analytics method, along with simple statistics. And we also observed that unsupervised machine learning and deep learning, they are not so used in the market. And we further backed up, or this insight coincide with some of the interviews that we performed. And actually this, if you can show Ben, yeah, thank you, the quotes. So basically the vendors coincide with our insights, and one of them remarked the idea that unsupervised machine learning is not very useful for predictive maintenance given the high rate of false positives, and also deep learning might not be very practical in most of maintenance applications. So this is all from my side, and back to you, Knud.
Sorry, I'm sorry. I realized I was on mute. My bad. So, one of the things in predictive maintenance that you do to evaluate how good a model is you put up a confusion matrix. Based on the survey responses we've received, we asked people to fill this out. This also assumes a couple of things, but by far the most case that happens the most often is that there is no fault and there is no fault predicted. So that by far in this is if you predict about in a 1 minute interval, you get to this. Now, only in 0.26% on average do you get a true positive, meaning you predicted something is wrong and it was actually wrong. So the machine was about to fail. In only 0.002%, the machine failed, but you did not see it. And in 0.13%, you predicted a fault, but it was actually not true. And so this kind of shows you where the industry is today. So if you then calculate some of the KPIs, the precision would be an important one. You see that the precision of the average predictive maintenance implementation is about 69%. And the other thing that you see is obviously, and this is assuming you calculate every minute, but in many predictive maintenance installations, you calculate more than every minute. So we've seen some, by the way, that's also part of the data set, but we're not showing everything for in the sake of time, not everything here today, that this number would go even higher when you do it on a second or millisecond basis. So I think, and this imbalance in the data is one of those problems that you have when creating the model, because you oftentimes have very little or few data points for actual failures, but you would have to have that in order to come up with a good model. And we'll discuss some strategies how that can be done. Now, in order to share some more research, one more thing from our research that we found over the last 5 years is that there are more and more data sources being used for building models. So you have pre-built models that is coming up quite a bit in discussions. You have first principles data, such as physics-based models. You have subject matter expertise, and these are kind of knowledge-based sources. Then you have maintenance logs, obviously. That's often a user input-based source. Then you have data directly from the assets, data from retrofitted sensors, data from the controller, from the gateway, from some historian. In many cases, a virtual sensor or a digital twin that kind of calculates some values. So this is a hardware-based sources. And then you have external data, whether for some instances it makes sense to have weather data in there or other things. And so we're seeing more and more people using all of these methods to come up with their predictive maintenance models. And so hybrid modeling, for example, I've taken this here as in the report, it is directly copied from the report, because this was where we also mentioned PARC, because they are doing hybrid modeling and they can much better explain what's happening here. But the idea is that you don't only rely on one or two of the data sources, but more. It's not always that easy and possible, but generally speaking, the market is moving towards more. Good. And with that, I would give it up to Markus to share how PARC is approaching predictive maintenance and some of the stories.
Excellent. So let me see if I can first get my screen shared. So you're all seeing it, I hope. Great. So good morning, afternoon, evening, everybody who's calling in and attending this morning. Morning in California, at least. So I'm very excited to share some of the work that we have done in the predictive maintenance area over the last several years and decades now for the next 20, 25 or so minutes. Before I do, I'd just like to thank Knud and Fernando and Alice and the rest of the Iot Analytics team for organizing this great event. We've had a great partnership with these guys so far, so we've been very happy to co-host and co-organize this. So just as a quick intro, so the name is Markus Larsson. I've been on the executive leadership team of PARC for about 4 years now. Have about 15 years of experience in various forms of corporate and startup innovation, and has for the last couple of years now really led the Pdm practice for PARC. And I'm joined by Vats, who is our head of business development for the PARC Predictive Maintenance operations, who's, as you can see from the slide here, also has a tremendously rich industry experience coming from the operational side of kind of industrial operators. And so just as a quick primer, because you all may not be that familiar with PARC, we are the advanced research and innovation arm of Xerox Corporation. People mostly know of us from, as Xerox PARC, well known for creating a lot of these breakthrough innovations that are used by everybody every day. So the whole personal computing paradigm, graphical user interface, laser printer, Ethernet, the mouse, and a bunch of those tools that we all use every day were either invented or kind of first conceived of or pioneered here. We're really operating as an open innovation center, and our core principle, or where we really shine, is sort of sitting in this intersection of advanced science and advanced technology and breakthrough innovation, meaning that we translate scientific and technical breakthroughs into practical and valuable innovations that people can take advantage of in their day-to-day work, typically from a kind of B2B type standpoint. And in doing that, we really help organizations like our parent or other partner organizations that we work with to rapidly respond and accurately respond to a rapidly shifting technological landscape. And we really try to stay true to this creed, right, which is one of was quoted or from one of our long now since retired famous alumni, Alan Kay. He was one of the main drivers behind the personal computing type of paradigm. Is that the best way to predict the future is to invent it, and that's really what we do and how we live our lives every day out here in Palo Alto. And just so from an agenda standpoint, I'll speak a little bit about the work we've done at Pdm more generally and some lessons there. And we'll go a little bit deeper around how to practically think about prioritizing your efforts, picking the right asset from the start, and how to sort of consider predictive maintenance as a concept and more than just a technology. And Vats will speak a little bit to that. And I'll give a couple of examples of some more technical details around prognostics algorithms that we've built during the time. And so, Knud mentioned earlier in the presentation that, the first time people really started to talk about, or you started to hear more about Pdm, I think is probably a more accurate way to characterize it, was, around 5 years ago. Well, we've been doing work in the predictive maintenance space since the late 80s, right? So we've really been investing in this for quite some time. And obviously a lot of this started with developing predictive maintenance technologies focused on preventing downtime for large-scale industrial printers. Many big moving components, and like with any manufacturing type operation, right? Untime is death, or downtime is death, and you just want to avoid it with any extent possible. So at that time, obviously, sensors were cheap, and machine learning was, a glimmer in the eye of some crazy academic somewhere, right? So a lot of that work had to be carried out through model-based reasoning, physics models, which is actually a practice that we really stay true to today, and has a lot of advantages that I'll get to shortly. But we have a deep and long experience kind of at the site with developing predictive maintenance technology. And we've done that now across just a wide number of industries. So printing is obviously, our legacy and where we come from. But over time, that has since expanded into, developing algorithms and deploying PDM solutions in industries with, across transportation, physical infrastructure, aerospace, oil and gas, chemicals, automotive manufacturing, consumer electronics, you name it, like across a whole number of manufacturing and heavy industrial sectors. So we've seen a lot, and we've learned a lot in the process. And so what are some of those key takeaways and learnings? Number one, and this might seem obvious, and we'll speak a little bit more about this, or Vats will speak about this in more depth, but you have to do your homework. It's not enough to just look at the data and develop a great algorithm and then kick it over the fence to users, right? You really have to understand how its performance will, enable better operational performance. And in that case, how will it intersect with operational processes, with business level requirements, with IT policies, and a bunch of other things like that. And importantly, how do you package and show that information, or show the prognostics or the predictions in a way that's actually consumable by the people who are going to end up using it? What's the user experience? And to use that buzzword, right? How do you actually showcase that, in what form, and in a way that really works with the workflow? You have to do that planning first before you start deploying or developing your technology, or it's just not gonna work so well. On the technological side, the first thing that we often look at in once we're kind of past the planning phase is like, what's the availability of and the quality of data? If it's there, if you have lots of it, and it's picking up the right, you've stored data of the right physical characteristics at the right frequency and the right signal band, great, because that's the fastest and quote unquote easiest way to actually get a functional and a great performing prognostics algorithm built. Problem is, more often than not, in the vast majority of cases even, we find that that's just not the case. So then, so if you need even better performance than what you can get from conventional machine learning type approach or statistics approaches, if you don't have the right kind or the right quantity of data, or even in the cases where you can't really make sense of it, we often then go and model the physics of the equipment that we're looking to make prognostics about. And that means not only modeling the physical operation of the equipment, it also means modeling the physical characteristics of the dominant fault modes. What do they look like? How do they manifest? What are the precursors? And how do they progress over time? And that's really important. I'll speak about that in a number of examples later. But really understanding what faults are the main drivers of downtime is key to build a high performance prognostics solution. And that'll also inform you, once you understand the physical properties of dominant fault modes and how they show up on equipment. It'll inform what type of sensors you need to procure and instrument onto the equipment if you need additional ones. Because what's there typically from as part of the control system, typically in the vast majority of cases, again, isn't enough to do really advanced and really high performing prognostic. So you often need to complement what's there with additional sensors or there's no sensing capabilities that can pick up other signals than what your control system cannot. And this is really the only way to solve what people often talk about as the cold start problem, right? How do you actually, if you don't have the right data to begin with and lots of it, how do you get a high performing prognostic solution built and deployed? And it is by building these models and deploying these sensors. And it's challenging, right? It's a specific skill set that requires a lot of training and practice and typically a lot of trial and error to actually get it right. So if you want to build this fast and you want to get results quickly, this is a bit of the plug, right? We would really urge you to work with somebody who's actually done this before and who has invested in these models and understands kind of how to make that a reality, how to actually build these physics-based models and of fault modes and of equipments and how to actually translate that into powerful prognostics. Because at the end of the day, there are no easy ways to do this and there are no shortcuts. But as Fernando showed in the slide before, if you do it right, the financial returns on investments into your operations of predictive maintenance, right, are overwhelmingly positive. But you have to do it the right way from the start. So these lessons speak, I think, mostly to the complexities around building high-performance prognostics algorithms and so on. But for any new PDM deployment, it also requires careful planning, analysis, and really thinking through a much broader set of questions than just the algorithms themselves. And to speak to that, I'd now like to invite Vats to take over. Vats?
Thank you, Markus. I hope I'm audible. Greetings, everyone, and thanks for joining from the different parts of the world and different time zones. We hope you are safe and your family is safe. We pray for the same. We at PARC have developed a Pdm Playbook. We have found that it is of utmost importance to see the pitfalls in the way of any technological solution. One of the biggest pitfalls, people generally take PDM as a technology problem, but we see it otherwise, right? Because there are many components to that. An accurate PDM solution should not only learn the machine behavior, but also should adapt the knowledge of the operators, maintenance practices, policies in place, etc., to accurately predict the remaining useful life of a machine or of the overall process health, which will eventually minimize the unplanned downtime. That's what our goal is. And I said our vision, our customer must achieve zero unplanned downtime with our PDM solution. That's our vision, and we're working on it. Simulation-based PDM solutions will not deliver expected accuracy, right? You've heard about a lot in the industry. Accuracy is really important, and hence we at PARC have developed a tailor-made PDM solution on IoT platform, which is based on true prognostics, and its accuracy is powered by physics-based model. It's not a mere simulation-based solution, right? Which means each asset in our solution library has a physics model, hence with the limited data set and with least number of sensors, as Markus alluded to earlier, we produce best results with highest accuracy as compared to other solutions in the market. Next slide, please, Markus. Another pitfall is confusion on the choice of assets. It's my favorite, right? Spent more than 20 years in the industry, right, in providing technological solutions. When I see from your contacts or from a user's perspective, I find myself cautious and a little confused. Which asset to pick, right? Where to go, right? A user needs guidance on feasibility, viability, desirability, and of course, is it strategic enough for my business, for our organization, right? And that's why we've got a tailor-made solution, as I mentioned earlier. It is very normal a user to be apprehensive about scope, return on investment, resources, and more importantly, impact of success. So Marcus, flip over, please. We understand all these worries are genuine, right? So to address that, we have developed a robust discovery playbook, which is shown on your screen right now, where we partner with our customers to understand their production processes, their infrastructure, data availability, quality of data, maintenance practices, fault modes, etc. I mean, spending weeks into the process, we create best path to success. We define a Pareto, which means which 20% assets or the processes will create 80% impact on the overall operations. So it's plans are nothing, as you can see from this slide. Planning is everything. The first building block for a successful PDM solution, or I may say an effective PDM solution, is a plan, right? Have we discovered what is required to deliver the desired results? Hence, we spend quite a number of weeks with our customers going through all their processes and develop this model. At the end of the day, a lot of ROI does depend on the performance of the prediction models. The return on investment of a PDM deployment is closely related to how well prognostic models are able to capture future failure events, not only current, future events, right? With that, I'll hand over to Marcus, who will speak more about some of our lessons for what it takes to build a highly accurate prognostic models. Marcus?
Thank you for that, Vats. So, so the first item I'd like to touch on is one, I think, quite common fallacy in how we see people generally approach predictive maintenance. Namely that more data is always better. PARC's former CEO and my former boss, he often liked to say that big data is not a solution; it's actually a problem. And I think there's a little bit of a misconception that I often see in that having the more operational data you have, it's always better, and you'll be able to get great performing prognostics just by having that. And that's just not quite true. So as an illustration for this, what you're seeing here on the screen is an algorithm that's monitoring the health of a ball valve, as you can see in the picture on the right there. The valve itself is used to control the flow of viscous liquid. And in normal operation, what happens with these is that the liquid kind of builds up and accumulates within the valve, which leads to more sluggish flow and sluggish behavior, to the point where the valve no longer is able to actually operate and kind of hits its end of life and production stops. And so what we've done here is sort of predict or associate the asset health with the closing time of the valve. So you're seeing on the right, as the closing time increases due to the accumulation of the liquid in the valve, the asset health declines almost linearly, right? Up until the point where, again, where it reaches its end of life and is no longer operational. So what's the takeaway? So why am I showing you this? Well, most control systems that we've come across have sensors that detect whether or not a valve is open or closed, that detects that in the order of 1 hertz or even 0.5 hertz, right? So it detects it once a second or once every other second or something like that. So as you're seeing how the even subtle changes in the valve closing time impacts the asset health and ultimately impacts operation. You can see how if all you can pick up is like step change of 1 or even 2 seconds, it really won't be very useful at all to help you predict when to shut down and flush and clean out a valve in this particular case. Now, most cases, of course, aren't quite that simple and straightforward, right? So physics-based modeling, the physics-based modeling approach is often much, much more complex than that sort of illustrative example that I just showed. Like this example of work that we did in partnership with and published in partnership with Panasonic here a couple of years ago. And so the work itself is for diagnostics of a factory robotic arm. And Panasonic, in this case, had a lot of control system data going back for many years, but it wasn't very well labeled. So they haven't been able to actually associate individual data points in that, which in this case was time series current data, with the state of normal or abnormal operations that you're seeing there on the ground truth chart to the left. So what they tried to do then was to run it through various forms of unsupervised machine learning algorithms, which is a fairly common approach to try if you have data of that kind, but it's not quite that well annotated. And I'll just, as an aside, say here that this is something that we come across all the time when we work with industrial partners to build these predictive maintenance solutions. That they have a lot of historical data. It's either, of the kind of that I mentioned earlier, that sensing frequency or modality isn't quite right or fit for purpose for PDM, or it's quite useful. It's just that it's not annotated, so it's hard to actually associate it with any failures in any meaningful way. Quality data of sufficient quantity to really build supervised machine learning approaches is, in industrial settings, just very, very hard to come by, or it's rare to come by. Either way, in this case, the unsupervised learning or machine learning algorithms were able to do, reasonably well. They were able to classify the state of the robotic arm with, 60, like 70% types of accuracy. So very similar to the performance that Knud referenced earlier in his section of the presentation. But those were just not deemed to be sufficiently good for actual deployment, for actually realizing the ROI that they had set out to go after. So instead, we started working together and built a number of physics models of the fault modes that were kind of dominant in this factory robotic arm, and importantly, just figured out how that would, or modeled how that would manifest in current, and how that was separate from the current shifts and the current levels. That would just be the result of regular operation or motions of the robotic arms, and reached really quite impressive results, right? So the accuracy, the clustering accuracy moved from on the order of 60 to 70%, right, to prediction accuracies, or the clustering accuracies in the high 90s. And we often see this, right? You get that, one level of performance with pure play machine learning approaches based on the data you have, but you can really get a step change by complementing that with, in this case, a hybrid modeling approach, right, where you augment the machine learning algorithms with the physics models and push your performance up into the high 90s. And at that stage, it's more than enough, and it's great performance for industrial deployment. And this work's published, so you can probably find it if you search through the literature. It actually won the Best Paper Award at the IEEE PHM conference here last year in 2020. So it's really important to understand the physics of what you're trying to predict. And I could probably give another 15 examples of this in work that we've done, because this is, relatively speaking, most often the approach that we take. But I'll note one added thing is that when we build these models and when we do put in place these predictive maintenance solutions, we always want to be able to give an accurate remaining useful life estimate and the diagnostic response as early as is possible, to give the operators as much time as is reasonable for them to react and respond to the fault. And to do that, we need to diagnose first and then prognosticate later, because you can't really forecast when an equipment is going to fail, credibly at least, if you don't understand how it's going to fail. And I'll just note too that this is not only important for technical performance, so performance prediction accuracy and time window and those types of things, but actually for operator acceptance of the tool output. We find that maintenance engineers or people who kind of run the day-to-day are much more receptive to what the tools tell them if they can tell them what's going to happen when, not just when some unspecified event is going to cause a problem for them. And so what you're seeing here is an animation of a bearing health algorithm. And bearings, as I'm sure a lot of people here on the phone or on the web, this webinar can appreciate, are, they're omnipresent in most types of operations. And their failures are quite infrequent, but can be quite costly. You often need to take equipment offline altogether. And if it's complex, that can take if equipment's complex, that can take a long time. If spare parts are not available, that can lead to very long time, long-term unplanned downtime problems. But the problem with bearings is that they are fine until they're not, right? So a 10-year-old bearing that runs the way it should looks not very different from a brand new bearing, just from an operations or from a measurement standpoint. So here it's very important to really dig down and understand the physics to be able to give as much lead time in the predictions as you can. So I won't go into the details of exactly how we did that, just in the interest of time. I'll just note that you can see here, that at the sort of 2.5-3 year mark, there is a rapid shift, or a very quick shift in the bearing health downwards. And that sort of manifests from the signals that we're measuring in this P&D. There's a shift in this PSD, power spectral density chart that you're seeing on the right, which allows us to give, a couple of months ahead of advance warning, sufficient to shut down production orderly or order spare parts or what have you. And that's always our approach. We try to get as accurate prognostics and diagnostics as we can as early as is possible. And the way we really accomplish that is through these physics-based models. So with that, I'd like to just hand off to Vats to take us home and talk a little bit how we're using these types of technologies and solutions to power our own operations, and then talk a little bit about how we can get in touch after the webinar too. So Vats.
Thank you, Markus.
Markus, if I can just say one word, we've already received quite a few questions, but feel free to put any questions you have at this point in the Q&A portion of your screen. We will get to them in a minute. Sorry, Vats, go ahead.
No problem. Danke, Knud. Thanks, Markus. And before I move on to this slide, this is one of my favorite slides whenever I make a presentation. And I would like to tag this slide to slide number 6, if you remember what Markus was trying to say, what PARC is, PARC and Xerox all about. And as they say, and I believe it personally, including my colleagues Markus and Sandra on the call, you do not learn to walk by following rules. You learn by doing it and falling over and over, right? So today, when we try to preach or we're making this presentation, believe me or not, we have practiced these moves every day, every hour, for months and years. Right? We have successfully tested our true prognostics powered PDM solution at various Xerox facilities in and out of the United States. From our experience, we can not only save 100%, hundreds of thousands of, but millions of dollars to our users, right? And more importantly, the precious production time that goes into unplanned downtime bucket, which is actually hurting our customers, right? So as you see this slide, there are 2 snapshots which are from our PDM solution with a real data feed. They're not just like a snapshot, they are the real data feed, right? Where we can monitor assets all the way from 36,000 feet, which you see on the right side, which is the dashboard showing you a production capacity of a plant over the last 6 months or 3 months or 2 months, or you can even see by minutes, trust me. I mean, like there are buttons over there. And overall asset health, how many of the assets are healthy, what's going on with the unhealthy assets, or the way this dashboard is showing their mechanical seals that needs attention right now. And then obviously there are a couple of fans who are kind of like, they're going out of the operation, right? And The screen on the left side is actually right away from 36,000 feet to the weeds level, where we can monitor up to the last dot in the production change to a specific asset, like for example, heat exchanger, or Markus talks about bearings in the previous lines. Our solution can predict both current and future health of the assets with more than 90% accuracy. The red box you're seeing on the left screenshot is the remaining useful life. And since our solution is powered by True Prognostics and it's physics-based, and our accuracy goes more than 90%. And not even that, we're one step ahead. What does it mean is our remaining useful life calculation is dynamic in nature. What does this mean is if you're running your plant or running your asset 24 hours, it's under load, the RUL will be X. If you reduce it by 12 hours, it'll be X minus delta X, right? With 90% plus accuracy. And that's where we feel proud. I wouldn't say we boast. We feel proud of our solution that helps our customer. So
hey,
what do you need?
We need to close it out. So can you?
What do you need? So you need to get in touch with us. We can help you in educating the technology, providing knowledge resources, case studies. We can discuss a pilot opportunity with return on investment estimation. And I personally encourage you to leverage PARC's artificial intelligence, machine learning strengths to make your operations even better and highly efficient. With this, on behalf of the PARC team, I would like to thank you, each of you, for your time and participation. Knud, back to you.
Great. Thank you very much, guys. This was really interesting. And we've received a bunch of questions. And for those who've asked questions already, we're happy to stay on a bit longer for whoever has time to discuss some of your questions. So to go directly in some of the questions, please feel free to ask more. There were a couple of questions coming in when Fernando and I were presenting on the market data that we presented. So quickly, I can speak to those. What part of the market size corresponds to analytics, machine learning services versus hardware, sensors, and network was one question. We have all of that in the report. Also a regional split and industry split, that was also a question. Without going too deep, analytics and machine learning services are getting much bigger. They're becoming a much bigger portion of the market. I don't have the exact numbers in front of me right now, but happy to follow this up and discuss. I'll show you in a second how we can get in touch. By the way, you can get in touch with us here on this link. And obviously, as Vats has said, you can send him a mail. Then there's a bunch of questions that have come in specifically for Vats and Markus on some of the things they've said. So I'm just going to read some out and leave it up for you, Markus, to discuss. So one question is, what should be the focus on cybersecurity in these developments? Markus, if you want to take that.
Sure. Sorry, I was trying to figure out how to unmute myself. Yeah, so cybersecurity is incredibly important for any IT project, really. But as soon as things start to touch proper operations, of course, it becomes of paramount importance, right? And in our experience, this is not just something that people say. It actually has such importance that it sort of trumps everything, and it should, right? There's a number of ways you can address this, and what we're finding actually, and I think this is even in the Pdm report, market reports that Knud will hopefully you guys will all purchase after this if you haven't already. That most people or the majority of operators actually don't connect their Pdm solutions to the open internet, so to speak. That they actually run them on-prem, then allowing for kind of data security to be the same as the type of data security that you have with the control system and the control of the plant more generally. I think the longer term trend is obviously to move this and many other IT and even OT technologies onto the cloud, and that's already happening in many cases. And the only advice I can give there is just work with those that are absolutely top-notch security providers. But there's no easy answer. But what we're seeing most people do is actually do on-prem installations, and that's what our approach is also built to kind of accommodate for that and allow for on-prem deployment as needed. So that's typically how we see things, people approaching that.
Very good. Just one quick thing. We would love to hear your feedback on the webinar. So Alice is going to put a link in the chat. So if you would be so kind to, it takes about a minute, not more, to fill out. Just let us know how we can improve next time and how this was for you, the experience. That would be really nice. Like I said, we're going to go over a bit because we have so many questions. Another one is, how do state-of-the-art predictive maintenance concepts or proof of concepts in research compare to existing industrial applications? What are the most recent developments in predictive maintenance on a research level? I mean, it sounds, Markus, like you guys have done quite a bit on a research level. So I'll ping that straight to you.
Yeah, wow. So it's a broad question, right? I think there's a couple of ways to answer that. So I think if you just look back 5-10 years, there's a lot of emphasis on, that's kind of when deep learning and the whole AI hype really started to hit full scale. And so there was a lot of emphasis on, just get as much data as you can, throw it into the, into a machine learning type of algorithm, and, magic will happen. And I think most sophisticated operations have moved away from that and are now more investing in these sophisticated hybrid type solutions that we were referencing earlier, and that's certainly what we've been doing for the last several years. I think and to sort of power that, what you're seeing is an explosion of new sensors and even new sensing modalities being considered and being implemented into solutions. So we've, for instance, experimented a lot with acoustic emission sensors that go high up into the ultrasonic frequency bands, for instance, to pick up faults that way. You're obviously seeing a ton of computer vision, and in some cases with, outside of the human visible type of spectra to analyze what's happening, the hyperspectral type of imaging type solutions. To see if there's something there that you can predict or use to predict faults. And lastly, use new types of sensors, right? So we're seeing, and we've experimented quite a bit with fiber optic sensing, which has a lot of benefits, not so much in picking up new sensor modalities, but that they are fairly practical to implement and deploy in certain environments where electrical sensors may be prohibited for various safety reasons, good ones, by the way, but fiber optical sensors just don't have those same types of problems. So I think you're seeing both research investment happening on the sensing side, on the sensor side, and on the analytics and the kind of model building side. And I'll add a third, which is a little more esoteric, but kind of actually ties back to the earlier question there, is that you're seeing, and this is sort of work that's happening, at DARPA and the kind of most advanced research institutes in the US, where people are actually using predictive maintenance like technologies. So, model-based reasoning, kind of understanding, or digital twin type solutions to understand whether there are security risks or breaches with autonomous systems. So, if your control system or your control of an autonomous drone, say, would imply a certain type of behavior physically in the drone, and that's really not showing up in the sensor data, you can probably conclude that something's happened and perhaps there's been a security breach that's led to that. So that's sort of a new kind of esoteric area that's starting to show up, but we haven't seen that much in industrial operations yet.
Very good overview. Again, if you need to drop off right now, we will be sending the recording of this in a few days, but we'll go on. And again, it would be really nice if you could fill out the survey. There were a couple of questions again for our market modeling. Someone asked if we have the software hardware services split in there. We do. And someone asked if it's a top-down or bottom-up approach for the modeling. We try to do this bottom-up, and we've been doing this, although it's fairly difficult to estimate all the revenues correctly, but that's how we do it. Happy to discuss more if you're interested. Someone asked, in your research, did you come across any predictive maintenance scenarios in which predictive maintenance was also being used to integrate with other business systems such as asset or labor management? Actually, we described in the report that this is a trend, that more and more predictive maintenance scenarios are being, predictive maintenance solutions are being integrated with other business systems, and ERP, I think, was it's the top type of application that this is being integrated with. But not only that, and this has obviously increased quite a bit. I think this is quite an area where predictive maintenance, yes, but it's not a standalone. It's more and more being integrated into the landscape. So that is something we're seeing. I don't know if Vats or Markus, you want to add to that, but that's clearly a trend. And asset and labor management is a part, particularly when it comes to remote asset and field service and so on.
No, I think that's exactly right. I mean, at the end of the day, to truly realize the value of the value potential of a solution like this, it really needs to or ought to integrate with those types of systems, ERP, planning, spare parts inventory, and those types of things. And I think, you know, the industry isn't quite there yet, but it's sort of an obvious next step towards a more wholly automated type of supply chain or operations, right? Where you can have an AI kind of at the heart of it, both detecting faults and then scheduling or dispatching people, or even procuring or staff, or even procuring spare parts as needed, and managing the inventory to kind of support that. We have a little ways to go to get to there, but that's certainly something that's going to come.
We have a few questions on the modeling. So one question asks, who is building the models, and are we as the user expected to know the difference between the different algorithms you mentioned?
Ideally not. So, I mean, obviously, then this sort of goes back to the reference that I made earlier, right? That from a user experience standpoint, it's really important that the output of the models and the output of the prognostics is communicated in a way that's understandable and that's credible and that's actionable to day-to-day users, right? Who are, you know, smart, educated, and knowledgeable people, but in their domain, not necessarily in artificial intelligence and in data science, right? So a good solution would not require that type of knowledge. Now, who builds the models? That's a question I think each organization will have to answer. You're seeing large operators, large industrials try to, and with varying degrees of success, build their own data science and prognostics teams in-house. And if you have the scale to support that, good for you. Most folks don't, though. And it is a very competitive market to hire people that has that type of skill set and that can really build these high performance models. We're lucky we're in the valley, we're fortunate to be in the valley and have this long track record in this world, so we're able to attract that great talent. But it's sort of, I think everybody has to make their own decisions, whether it's a strategic investment for them to build this capability in-house or to buy it from somebody who has built a team already, the algorithms or the models already, and who are able to deploy them for their customers' operations.
Good. Another question that came in: how do you label time series to prepare supervised learning approaches?
Well, that's getting into a little bit of a technical detail that I'm unfortunately not so much involved in myself, but I think this is one where we'd be happy to have connect with one of the folks in our technical team who can speak to that more, I think, precisely than I can. I mean, at some level, you want to correlate anomalies in the time series data with specific faults or specific events that you're interested in tracking, and then have those various time series line up. But again, I'll probably it's probably better to have somebody in the science team dig into that a little bit more. So if you want to understand that a little bit better, absolutely reach out to Vats and we can have something organized to talk about that more.
Sure. Yeah, just to add on that, Markus, I'm glad that you touched upon that. But that's one of the specific features, right? We always absorb or pulse data from the OT system available, and they all are time series stamped, and that's how we include making sure that the right event right time when the event happened is being captured, right? So whether it's PLCs, SCADA, or DCS, the inputs are coming live to our system.
Good. We'll go for a few more minutes. We still have plenty of questions, actually. We probably won't be able to get to all of them, but we'll do a few more. There are a few very specific ones, and I would suggest for those people to reach out to the team. So there's a couple of people that have indicated they're interested to hear more about your bearing example. Markus, I would think that we would, maybe it's better to take that offline.
Yeah, please don't embarrass me by getting too deep on that. I think that's probably best for everybody.
There's also some question around how do you scale this prognostic remaining useful life, because that's obviously always a thing that comes up, and you're very successful on a small scale, and then there's so much, in IoT in general, there's so many, such big complexities in scaling this. So I don't know if you want to provide any commentary on that, because I think it's a topic that a lot of companies are struggling with, because a lot of them are in an earlier phase than the scaling phase at this point.
Yeah, and there's no denying that's been one of the challenges, and it continues to be one of the challenges for, as you say, IoT generally, or kind of the intersection of IoT and AI generally. I think we believe that physics models is actually a way to get you there faster, right? You can build parametric models of how, say, a pump operates and how common fault modes in that pump manifests. And you can do that more or less independently from, sensor SKUs, and understand having like a complete detailed read on exactly what sensor is available in each individual pump and each individual pump SKU from every OEM and whatever materials they're made in, etc. Right? So building or having that library of pre-built models is actually a way to get you to scale faster. I mean, there's no shortcuts there either, right? It's not like, oh, you built a pump model, so now you're good. You can model every pump with great accuracy. You always need to tune the models, and you always need to customize them to the environment that they exist in, and tailor the specific sensor data streams that are either available or need to be brought in separately, right, from retrofit instrumentation and so on. So there is always a bit of work there that it's just not avoidable. But there are definitely scale benefits to going the physics-based route that are harder to come by if you're doing pure-based data science approaches. I mean, on the other hand, like a pure play machine learning approach is sort of more scalable in itself, right? In the cloud or whatever. It's just not as scalable on the ground with actual equipment once you have it deployed. So, no shortcuts, but I think that's one way to think about it.
Good. Someone wants to know, do you deploy your solution in different IIoT platforms or environments like an edge device, or do you deploy on a specific platform?
We can currently work on AWS and Azure. But it's sort of one of those things too. It's about scale. Where do you want to take that investment? Do you want to deploy it on others? Does that make sense? And how much return can you get from that? And at some level, we're trying to modularize this like everybody else is, so you can be relatively independent of what ultimate platform provider you're working with. But there's only so far you can take that, right? So there's some what's the word? There's some trade-offs there, I guess. But certainly the large providers, you ought to be able to do this for, and that's certainly certainly what we do.
Good. Fine. So we'll squeeze one or two more questions in. Unfortunately, we can't do all of them, and I think Markus Vats will try to follow up with those who have not done it anonymously. Some of the questions are anonymously. One more question here is, how do you work with the paradigms and fears of field specialists when incorporating a predictive maintenance technology? So moving a bit away from the technology discussion to the fears of. You're smiling, Markus. So I'm sure you.
Well, yeah, no, I'm laughing. I mean, this is not. It's not only a technology question, like you say, and it's certainly. It conforms with what Vats was speaking to, and I ask Vats to weigh in on this too. But I'll just say that this is not even a predictive maintenance problem, right? This is a general technology problem. A lot of people who are, particularly recently, right, when the rise of AI has been all over the news, and will we ever have jobs anymore, et cetera, et cetera. So people are typically both, I think, skeptical technically that something will ever work, but also there may be some fear in there that's like, well, is this going to be a robot that's going to replace me for working? And I think the only real way to answer that, or the only real way to respond to that fear or that uncertainty or that doubt or whatever the label you want to put on it is to have them along through the process, right? So you work together with those stakeholders when you design and implement a solution, so that their voice is heard, and their concerns may or may not be addressed through that, but at least they're kind of part of the change management journey, if that's a phrase you want to use, right? So that you can have them as stakeholders throughout that process. Yeah. And B, really, these solutions are not, at least not yet, and probably not for a fairly long time, like a wholesale replacement of people, right? This is intended to augment and help them do their work and give them more information and more tools to make better decisions, and to ultimately help the performance of their employers and of the business that they're working in. So there's a little bit of a dynamic there that you have to manage, but our experience is that it's best to really involve them in the process early. I don't know, Vats, if you have anything else you want to.
Yeah, sure, Markus. Thanks. Actually, this is not the first time. That's why Markus and I were smiling. We've been hearing it, seeing it every meeting we have had so far. Trust me, for Pdm right now in our career as well. There is no need to fear, because those field specialists, I call them knowledge experts, right? You cannot replace their knowledge. It's just like Pdm is another tool that's going to help them in making their decision process more effective and way far more accurate. That's how I take it. If I were one of the field specialists, okay, I got a solution. I know how my machine is going to behave down the line 6 months. I can do better decision making right now. So I would not consider this as a fear in course, right? The fear they've got. No, it's just a decision making tool, and also it's a tool that gives you extra edge towards keeping safety at your plant. That's how I would see it.
Good. I mean, if I maybe small thing to add from my side, because we obviously see that in our research all the time as well. But I think I skipped the outlook part because I wanted to get to Q&A, and I think this was a very good and important discussion. But the one thing I would say from a research point of view, we've seen that people, due to what happened with COVID and work from home, people generally speaking have become much more open to technology. I think this is a mindset thing that goes to the average field technician, and we see this. And so I personally believe that technology implementation is going to be a little bit easier in general in the next years because of what we've seen and how this has helped. And so, and maybe also on that note, in the surveys we're doing with CIOs and other people, we see that they all expect a digital wave coming. Predictive maintenance will be part of it. Not the first priority, that's clear. There's other things that are more important, but it's becoming more important, and the wave is coming. Hopefully soon. Hopefully as soon as we are back to some normal, in some countries more than others, apparently. But I think that's a optimistic and nice note to end on, I would say. So my suggestion is we leave it here. I know there are some questions that we haven't been able to answer, but we'll follow up. And again, for those who are dropping off now, please leave your feedback. We listen to it. We try to make it better next time. So yeah, thank you guys very much. Thank you, Vats, Markus, Fernando. And so everyone watching, have a great rest of your day and be in touch.